towards the end we started talking about Bayesian inference, but we did not do much. We just talked about different components of Bayesian inference. We introduced that there is something known as the prior, there is something known as the likelihood, there is something known as the posterior, and then there is something known as the evidence from the Bayes law. Prior is basically supposed to be a distribution that should model your prior belief before you have observed any data. And the example I gave was before, when you registered for this course, you might have some prior belief based on some other interaction. Then the likelihood is supposed to be dependent on the data generation process, and that is why it has a D term there. And the likelihood, the form of likelihood depends on what problem you are solving. For example, if it is a coin tossing example, then it is Bernoulli or binomial depending on what you are trying to find out. Posterior is supposed to be a combination of your prior and likelihood. And the example again I gave was that after you do this course or maybe midway through this course, your belief about me will be a combination of what you believe before you registered for this course, and will be governed also by the data you collected by using your 5 senses till that point in this course. And these are the things that we talked about. And the last thing we talked about was the concept of maximum likelihood estimation, and we said that I want to find theta that will maximize my d, that with probability of d given theta, that will maximize the probability, which means you are asking the question, give me the theta that best explains the data, and that is where we stopped, right. So, today we will start from exactly that point. Okay. So, we were talking about maximum likelihood estimation, which I will not every time not write the full form, I will just refer to it as MLE. This is a very standard term that is used for to denote maximum likelihood estimation. And here, if you remember, what I wrote last time was that theta star, which is the best theta, a point estimate, you will get a number, not a distribution, is equal to, you will try to maximize. So, basically the theta that maximizes your likelihood. Okay. This is what maximum likelihood estimation is all about. Okay. You just have to solve a maximization problem or an optimization problem. So, now let us take one example today, and the same example from last time, which is the coin tossing example, and for that let us try to see what is the value of theta that I will get if I solve it using maximum likelihood estimation. And then we will solve the same problem with maximum a posteriori estimate and also with the Bayesian. We will find out the predictive distribution and we will compare all of that, and that is all we will do today. So, today we are only going to talk about the coin tossing example from different perspective that we introduced slightly in our last lecture, just to understand, to get a feel that how these things are giving different results and if there is a relation between the two and so on and so forth. Okay. So, that is what we are going to do today. So, the example we took last time was, the coin tossing example. So, suppose we toss a coin n times and the data that I get is D, and let us say head, tail, tail, head, tail. Okay. Okay. So, I have tossed it n number of times, each time I will get a data, either a head or a tail, and that is what I got, and that becomes my data set, right. what was the problem? Because this is the data observation. Now, what do I want to estimate? Let us say probability of head, that was the same thing last time, right. So, I want to estimate. So, the objective is find probability of head, okay. And this I will denote by mu, okay. So, in the generalized notation, mu is my theta. In the top expression you see theta, that is my mu for this example, okay. So, therefore, I can write, as I said, theta is equal to mu for this example. For the different problem, theta might change, theta might be a vector and all those things, but for this problem at least theta is a scalar, a mu. Clear? The problem statement is clear. So, now I want to solve it using maximum likelihood estimation. For that I will need the likelihood, probability of d given theta, right. So, and we already saw how the likelihood looks like last time. So, for this problem, so the observation 1 is that observation, actually there is only one observation, so that is fine. The outcome of the experiments are independent, right. What is the experiment? Tossing the coin. Outcome head or tail. Outcomes mean in the first time whether I will get a head and tail will not influence next time whether I am going to get a head or tail. You can take a coin, right, it does not matter. The second toss is independent of the first toss, okay. So, that is my observation. So, therefore, probability of d given theta, which is the likelihood, will be equal to product of I equal to 1 to n probability of x I given theta, right. That is my likelihood, right, and theta is my mu. Remember that theta is my mu, don't lose track of that. I am trying to write it in a generalized way, and that is why I am using the notation theta, but theta is your mu. So, do not forget that, okay. So, now what is probability of xi given theta? It is, what is the distribution? Bernoulli, right. So, it will be, now I will write, instead of I can write theta, but let me write mu now, bring in mu. So, it will become mu to the power xi multiplied by 1 minus mu to the power 1 minus x I. You agree to this? No question on this, right? This is obvious. Okay, and you can check it, put xi equal to 1, you will get probability of head, put xi equal to 0, you will get probability of tail. And if you do head plus tail, you will get 1. That means it is the PMA, okay, for a single coin toss again. Okay. So, this is my likelihood and this is what I will try to maximize, correct. Now, instead of now this is a small trick, I mean quite obvious, that I do not like this expression. So, what I can do is I will need to simplify it, and the obvious one is there is product, I will take log, right. So, I will work with log likelihood, because this is my likelihood, I am taking log of that, that is known as log likelihood. And this is a thing you should always keep in mind, that throughout this course the use of log will be tremendous, and the reason is that probability varies from 0 to 1. So, often those numbers are small, specifically if there is something in the power, and it becomes very difficult to because it can be give underflow or overflow problem, something by 0 or very small number, computer will not be able to track that, right. And so, what we work with is log of that, which will give you a nice number that you can work with. Okay. So, that is from a programming point of view we will do. So, for convenience, we choose to work with the log likelihood. Okay. And this log likelihood is, I will denote it as L of theta, which is equal to log probability of d given theta, which for this problem will be equal to, you will take a log of that right hand side. So, what will you get if you take log of that right hand side? The product will become summation, right. So, it will be summation of log whatever is inside, and whatever is inside is log a b, you can write it as log a plus log b, and then there are some power which will come outside, like log of x to the power a is equal to a log x. So, all of those things you can do. So, this is equal to log, and then what you have is so summation I will do later. First I write the whole thing, I equal to 1 to n mu to the power x I 1 minus mu to the power 1 minus x I, which then is equal to summation I equal to 1 to n, and then I will take the power outside. So, x I log mu x I log mu plus 1 minus x I log 1 minus mu. Nothing difficult, simple, right? Simple obvious calculation, just taking log and then using the log property, right? Then log of mu, is it a function of I? No. With change of experiment your mu does not change. So, that can come outside the summation. Same for log 1 minus mu, that is not changing with I. So, that is like a constant for us, unknown but constant. So, those things can come outside the summation, and that will give us a simpler form. So, I will get log of mu summation I equal to 1 to n x I plus log of 1 minus mu summation I equal to 1 to n 1 minus x I. Clear? Now, I have a question for you, all of you. So, can someone tell me what is summation of x I? What is x I? Let us start with that. What is x I? 0 or 1. When will it be 0? If you get tail. 1, when you will get?
Number of heads and number of tails.
So, 1. So, now you are doing a summation over n number of times. What will you get? Each time there is a head you will put 1, each time there is a tail you will put 0. So, ultimately the summation will be equal to number of heads. That is why we do 0 and 1 for this case, otherwise this property will not hold. So, that is the reason 0 and 1 is there. Okay. So, there is a reason that 0 and 1 has been chosen to make our life easier. Had I taken minus and 1 1 1, then I would have been in trouble. I mean, I can still do it, but then this might not make that much sense. But again, if I take minus 1 and 1, the form of Bernoulli itself will change. This will not be the form of Bernoulli again, right. So, that is fine. Okay. So, now we note that summation of I equal to 1 to n x I, this denotes number of heads, and similarly summation of 1 minus x I will denote number of tails, because every time you get a 0 that will be counted, every time you get a 1 that will not be counted, and you cannot have a fraction like 0.5 and all those things you cannot get. Clear? So, then and also summation over I equal to 1 to n 1 minus x I, not I is at the top, right, in my notation, x I is equal to number of tails. Okay. So, what I will do is I will introduce a notation. Let us say this is equal to n h, which is number of heads, and this is equal to n t, which is number of tails, right. So, then we write this L theta in this with n h and n t. So, therefore, L theta now becomes n h times mu log mu, right. Log mu plus n t times log 1 minus mu. Okay. So, this is the final form that I will work with. I have simplified things and all those, and I have arrived at this form. Okay. So, this is what I will work with and try to find what again, remind me what is the objective again, because I did all this calculation, but what is the objective? Likelihood to find out theta, which is mu. So, remember, do not lose track of the objective. The objective is still the same, to find out mu. Okay, we are doing this calculation, but the objective remains the same. So, therefore, let me give some equation numbers, right. Let us, where is, let us see, yeah, let us call it equation 1. Okay. I will call this one as equation 2, then the likelihood. Okay. Then let us call it 3, although I will not need 3, but I will definitely need 4. Okay. Repeat the first one, right? You asked what is the first one, right? First one is this one. Okay, the obvious one. So, now with this setup, for finding theta, which is equal to mu, using MLE, we rewrite equation 1, which is my theta star is equal to argmax theta probability of d given theta. We rewrite equation 1 by considering L theta, which is my L theta is my log likelihood, instead of probability of d given theta. which is my likelihood, right. So, that means my equation will now becomes theta star is equal to arg max theta L theta. Okay. Clear? And this will be my equation 5. Okay. Now, I want to maximize it. I have the form of L theta in equation 4. How should I, how do you maximize? What should I do? Take differentiation and make it equal to 0. That is how you maximize or minimize. The derivative is equal to 0. So, therefore, d L theta d theta, which is basically equal to d L mu, theta is my mu, d mu, which is d mu, not theta, d mu, which is equal to d mu, and L mu is equal to this expression. So, I am using equation 4 here. So, that will give me NH log mu plus NT 1 minus log of 1 minus mu. So, NH log mu plus NT log 1 minus mu. Okay. And let me write it down that this is from equation 4. Okay. And this whole thing should be equal to 0. So, this is supposed to be equal to 0, right, which implies, so now let us do the derivative. So, I will get NH by mu, log mu is 1 by mu, derivative of that. So, which implies NH by mu minus, because there is a 1 minus mu, so that minus will come, NT divided by 1 minus mu is equal to 0, right, which then implies we can take it to the right hand side. So, 1 minus mu NH is equal to mu NT, okay, which finally implies, not finally, but anyways, NH plus NT mu is equal to NH, right. So, whatever is having mu, I have taken it to one side, taken mu common, and that will give me NH plus NT, and on the other hand side there is 1 times NH that remains, right. Now, what is NH plus NT? Total number of experiments. So, this is nothing but n. So, which finally gives me mu is equal to NH by n, right, which is the common sense answer. I mean, without doing all this calculation, if I have told what is the probability of head, you would have counted, okay, I got head 5 times out of 10, so it is 0.5. So, that is the important conclusion. Maximum likelihood estimation gives you the common sense answer. Now, common sense answer may not be the correct answer, but that is a different story. So, we will come to that. Okay. So, the important conclusion is that MLE yields the common sense answer. Okay. Now, let me try to argue why common sense answer might not be a correct answer. Okay. So, suppose I have a coin, I toss it 3 times, I get 3 tails. right. So, based on that, based on the common sense answer, what will be the probability of getting ahead? 0. Now, I ask you the question, okay. Now, I will toss the coin for the 4th times. Do you think that the probability of getting head the 4th time will be 0? Right? But the common sense answer that we got will tell it to be 0. So, that means there is something wrong that is happening here when you are only taking decision based on your data. Because you have 3 data points, you get probability of head is equal to 0 because there were 3 tails, but and that is okay, that is common sense. But then if I now ask you, okay, I am going to toss the coin a 4th time, what do you think is probability of head now? If you say it is 0, I do not think you will say that, because you know that okay, 3 was a very small number, it is not enough, there is a chance that it might come out to be head, right. It is even possible that the next 3 will be head, even that is possible. But that logic that you can build on your mind is not getting reflected in the common sense answer that we are getting using maximum likelihood estimation.
So it may happen that the coin is biased.
It may happen, but even with a biased coin, it is so biased that every time you are getting tail. I mean, let us change this example and take your example. Let us say with 3 toss, you will not trust it, right. Even if with 3, I do not think with 3 tails, I do not think anyone will say that the 4th one will also be tail with probability 1. You might say that it will be tail with probability 0.8 or something like that, but 1 is a very strong statement. I will say, I will not even say the next one will be probability of head with probability 1, even if I get 10,000 tails. Even in that case, there might be a 0.00001% chance that okay, the next one might still be head. Until and unless you do it infinite number of times, only then you can conclude that the coin is completely biased with probability 1. A biased coin is not 0.5. Now, then there comes the magnitude of bias. It might be biased so that 0.6 and 0.4, 0.7 and 0.3, all of those are biased. But telling it is 0 or 1 is an extreme statement, right. And that I do not think anyone will say, specifically not if that is 3 toss. Okay. And also, let me ask this question also. So, suppose I toss a coin 3 times, get 3 tails, I ask you what is the probability of getting a head in the 4th toss. Okay. The next thing is I toss the coin 3000 times, I get 3000 tails, what is the probability of getting the head the next time? These two probability as per this common sense thing MLE will be equal to 0. But if I ask you, you will say that no, in the first case the probability of getting a head should be higher as compared to the next case. That also is not getting reflected here. So, that is the challenge, that is the issue with maximum likelihood estimation, that is the issue with frequentist approach. This is known as frequentist approach, by the way. Okay. And that is where Bayesian comes in, and I will show you next that with Bayesian this problem automatically goes away, you do not have to do anything. Okay. So, next let us try to solve the same problem with Bayesian, and we will try to solve it with Bayesian, and also we will try to find the map estimate both. Okay.
Is the problem with the MLE method or the data?
MLE method. The data might come out, 3 toss you can get tail. So, it is problem with the MLE method that it completely trusts the data. Your data might also have noise. In this case there is no noise, but when you go and measure real data, there will be noise. MLE will overfit the noise also.
So the problem with MLE is that
It is completely on data, and not only data, I should say it is completely on the measurement data, and measurement data always will have some noise. So, it is also relying on that noise, and it will overfit that noise. Okay. So, that is the problem. So, next we go to, or we try to at least solve the same problem using Bayesian inference. Okay. So, next we want to solve it using Bayesian inference. So, what is the law that I will use here? Bayes law. That is the only law. So, I know that probability of theta given data, that is what I want to find, mu given data, and I know that it is proportional to probability of theta, probability of d given theta. Agreed? Proportional to, because I am not writing the denominator, okay, which is probability of d, that I will not need. Now, probability of d given theta remains as it is. So, what was probability of d given theta that I got? Probability of d given theta is equal to product of I equal to 1 to n mu to the power x I 1 minus mu to the power 1 minus x I, right. This is from which equation? Somewhere I wrote, I guess I gave equation 2. So, this is from equation 2. So, the same simplification that I did with log, I can do the same simplification even without log. Why? Because there is product in power, which will become summation in the power. So, x to the power a multiplied by x to the power b is equal to x to the power a plus b. So, I can use that thing, right. So, what will I get if I do that? There is a summation, the product will go to the power and become a summation. So, you will end up getting mu to the power summation x I sum over I and 1 minus mu to the power summation over I 1 minus x I. You agree to this? There is nothing difficult, right? I am just using the power sum, I mean product of power becomes summation in the power, right? Product in the exponent becomes summation. And I will use the same thing, summation x I is equal to nh, summation of 1 minus x I is equal to nt. So, that I will get again, which is equal to mu nh 1 minus mu n t, right, and this is my probability of d given theta. That let me write. Let us call it equation what 5, 6 or something like that, 6. Okay. If I miss 5 somewhere, write, give any equation for number 5. Maybe the answer, the final answer you got MLE, you call it 5. Okay, this is there. Okay. Okay. So, it is mu to the power nh 1 minus mu to the power nt, right. Now, I need a prior also, and that is a tricky part. I have not yet covered prior, remember that. So, prior. So, prior is supposed to be a distribution, okay, and I can take any distribution in theory based on my prior knowledge. I am going to take beta distribution as my prior in this case, and there is a very good reason for that. The reason I am going to take beta as my prior is because right now my objective is not going to go into details on how to model prior. Rather, my objective now is to show you that with a prior things can change and things will become better. So, that is why I am selecting a prior that will make my life easier, that will allow me to do this calculation analytically. With some other prior, this calculation will not be, it will not be possible to do this calculation analytically, and I will have to use some sampling scheme to sample. Okay. But with beta prior, it will be possible to do this thing analytically, because, and I will cover it in the next lecture in details, not beta, but this term I am going to introduce now, because beta is a conjugate prior of Bernoulli distribution. Remember this term conjugate prior? This we will discuss next lecture and the lecture after that when we talk about prior. So, right now I am just throwing this term at you, that beta is a conjugate prior of Bernoulli distribution, and when it is a conjugate prior you can do things analytically. And right now I am going to take it as a beta prior, because my objective right now with this problem is to not to introduce about prior modeling and all those things, rather my objective is to show that how the problem of MLE can be solved with Bayesian, and it will be solved with anything you take it in Bayesian and model it will be solved. Okay. So, since that is the objective, so I will take a prior which is of beta distribution. Okay. So, I will take beta. So, I will make some changes here. So, prior I want to take, which will be probability of theta. I am intentionally not completing the bracket. It is beta with certain beta like Gaussian has two parameters, mean and covariance. Uniform has two parameters, lower limit and upper limit. Bernoulli has one parameter, mu. So, every distribution has some parameters. Beta is denoted by two parameters, a and b, or alpha and beta. Okay. These two are known as, I think if I am not wrong, check it, I think scale and shift parameter, and both are supposed to be greater than 0 and real. Okay. So, beta a comma b. So, I have now beta has two parameters that should come on this side also. So, this I will denote as this, where eta is known as hyperparameter. Eta is known as hyperparameter. Why the term hyper? Because remember, theta is my parameter to start with. So, it is parameter of parameter. So, parameter of parameter is known as hyperparameter. Okay. And what is eta? A and b. Okay. Beta, how does it look? Well, the total distribution I will not write, because that is not needed, but the main thing that is needed is the distribution form. What you do not need is the normalizing constant. So, I am not writing the normalizing constant. So, the form I am giving will not integrate to 1, you have to multiply by some factor to get that, but the form of this is, if it is over theta, right. So, theta to the power a minus 1 multiplied by 1 minus theta to the power b minus 1, which is equal to, what is my theta? Mu. So, I will write it in terms of mu. So, mu to the power okay. So, this is the beta distribution, unnormalized. So, if you integrate it, you will not get 1. What will you get if you integrate this? You will get beta of a comma b. So, the normalizing constant is beta function, not beta distribution. So, the normalizing constant is 1 by beta a comma b. Okay. So, you can check in Wikipedia, all those things are there for beta distribution. Okay. You can read the book chapter 2, all these distributions are there. I do not want you to remember the exact form of the distribution, not needed, but you should be able to identify the distribution. For example, you do not need remember beta, that is fine. You forget it, whether there is a minus 1 or a minus 10, fine, I do not care, and it will not matter more importantly. But you should remember that mu to the power something and 1 minus mu to the power something represents, has some similarity. This should ring a bell that okay, this looks like beta, and then you go and check the internet, that is fine. But so you should be able to identify but not remember. That is the main thing. There is no point memorizing this thing, but you should be able to identify, and you will be able to identify if you solve many problems, right? Because then these things automatically comes to your mind. Okay? So, there is no need to memorize these things, but you should be able to identify. Okay? Clear? So, this is my beta distribution and this is my prior. So, now I want to find out my posterior. So, with this setup, my posterior is equal to probability of theta given d, which is proportional to prior times the likelihood. Prior is equal to mu to the power a minus 1, 1 minus mu to the power b minus 1. Okay. So, this is my prior. Multiplied by what is my likelihood? Mu to the power nh 1 minus mu to the power nt. nt, right? Clear? Now, you do the product, what will you get? So, probability of theta given, where I am writing again theta is nothing but mu. This is proportional to mu to the power nh plus a minus 1 plus a minus 1 minus mu to the power nt plus b minus 1. Okay. And now, what is this distribution you got? Just as I said, just by looking at it, can you tell me? Beta distribution. What are the parameters? So, this is equal to beta nh plus a nt plus b. And with this, I have done two things. The first thing is, I have indirectly defined what is the conjugate prior. A conjugate prior is a prior where or for which the prior and posterior has the same distribution, same family. I mean, the parameters will change, but the distribution will not change. So, that means that let us say if your prior is coming from x distribution or some distribution x, then your posterior should also be from the same distribution. So, only the parameters would get updated. This will not happen if I instead of beta take something, let us say gamma. So, if I take gamma as my prior, my posterior will be something else, it will not be gamma. And so, gamma is not a conjugate prior of Bernoulli. So, conjugate prior depends on the likelihood. So, when I say beta is a conjugate prior, it is a conjugate prior of, or it is a conjugate prior when the likelihood is Bernoulli or binomial. If my likelihood is of some other distribution, then beta will no longer be a conjugate prior. Okay? And as far as I know, I do not know any distribution which has more than one conjugate prior, right. But there are cases like Gaussian, if you take some parameters to be known, the conjugate prior is Gaussian. If you consider everything to be unknown, then it becomes Gauss inverse gamma. So, depends ki how you are doing it, whether everything is known or unknown, but otherwise it is mostly unique. So, for example, the conjugate prior of Bernoulli is beta, or binomial is also beta, but Bernoulli has only beta as conjugate prior. Okay. Now, how will you know what is the conjugate prior of what? Again, you do not need to remember anything. There is a big table, just type conjugate prior in Wikipedia, you will get at least 20 distribution, each will have their conjugate prior. So, what is the conjugate prior for beta? For beta, I do not know, I have to check. I do not remember. I also check Wikipedia, as I said, what I am suggesting I should follow, right? I also do not remember. Okay. I know the obvious ones because that we will use in this course, others I do not remember because I do not use it. Okay. So, yeah, so we got updated and this is what I got. Okay. We will work on the more on this part, but first since I have this, let us go and find out the map estimate, which is the maximum a posteriori estimate. Let us find that first. Okay. So, now, so first we focus on maximum a posteriori estimate, also known as the map estimate, and map again is a very standard term. Okay. We will use it throughout this course. How will you get the map estimate? Remind me, what will you maximize now? The posterior. So, this was what you will maximize. Okay. And you will only work with the unnormalized one. because the normalization constant is not a function of whatever is on theta, right, in this case. So, which means you are trying to now find out theta star by maximizing probability of theta given d, which is in this case is equivalent to maximizing let us call it L map theta, which I will define now, okay, where L map theta is equal to log of mu to the power nh plus a minus 1 minus mu to the power nt plus b minus 1, right. Take the log, what will you get? In fact, I can ask you what do you think will be the answer? Let us forget about all of this. What do you think will be the answer you will get after solving this? You can relate it with the MLE actually. Yeah, log, no, not only log, maximize and then find out theta map. So, that one. So, obviously, in the numerator you are very sure it will be nh plus a minus 1, and the denominator it will be nh plus a plus nt plus b minus 2, because whatever we got it should look like same, just the power is changing, but let us do that. Okay. So, yeah, so this is equal to, so L map theta is equal to nh plus a minus 1 log of mu plus nt plus b minus 1 log of 1 minus mu. Okay. And you will try to maximize it. So, following same procedure as before, dl map theta by d theta is equal to 0. This implies, I will now take derivative with respect to mu, because theta is mu. I will get what? nh plus a minus 1 by mu minus nt plus b minus 1 by 1 minus mu equal to 0, which finally will give you mu is equal to, you do the calculation one small step, but I think it will give you this. Where n is nh plus nt. Okay. So, this is what you will get, and this is my maximum a posteriori estimate, and you can clearly see that this is different from the MLE until and unless a equal to b equal to 1. So, as a special case, if my prior is beta with 1 comma 1, which is known as non-informative prior, which means that prior is not giving any information, and if the prior is not giving any information, your results should converge to the MLE estimate. So, if you use a non-informative prior, which is beta 1 comma 1, then you will end up getting what you generally get, which is the maximum likelihood estimate. I will repeat. So, beta, what is A and B in beta? Hyperparameters. Who will give you those parameters? You have to take. How? Based on what? Based on your prior knowledge. If you have some prior belief, you will tune those parameters to match your prior knowledge. Now, let us take a special case, which is beta a 1 comma 1. So, a equal to b equal to 1. That is a possible prior. Put that into this expression. In the numerator, what will you get? In the denominator, which is my MLE estimate. which means your MLE estimate and map estimate are becoming prior, and this is happening because beta with 1 comma 1 is a non-informative prior, which means it does not give any information. So, if the prior is not giving any information, what will be your decision based on? Only data. So, it should be equal to your maximum likelihood estimate. Clear? I will obviously write it down, but
So, sir, how in this case, in such cases, we can take A and B, which give us maximum information, like best A and B values?
so that's on you, right? So, let's say you and I are solving a problem. Now, you are much familiar with the problem, I am not. So, your prior should be better than me, correct? So, the prior will not be same between you and me. So, if there is an expert in a domain, then the prior taken by the expert will be much better or stronger, I will say better, I will say not stronger, than a prior taken by a novice in a domain, correct? It is obvious. Okay. So, selecting prior is important. If you do not select proper prior, even Bayesian will go to waste, specifically if you are doing map estimate. I will show you later that this issue does not come with the complete Bayesian thing, but this issue do come in this case. Okay. So, let me write it down. So, therefore, mu map is equal to NH plus A minus 1 by N plus A plus B minus 2. Okay. Now, what do you think this A and B are doing? Right, but can I say that A and B are my pseudo count? So, before pseudo count, because I am counting head and tail. So, A and B are like my pseudo count, those are the count before I have observed anything. In my mind, right, they are not, you are not actually counting it, but they are like pseudo count, they are acting like count. So, A and B are kind of like the pseudo count. Okay. So, A, B are the hyperparameter and act as pseudo counts. Okay. What will happen if A and B are very large? Let us say A and B are 10 to the power 20 and your N is 20. What will happen? You have a very strong prior. Your likelihood data will not matter.
Less dependence on
Data. So, the strength of your prior in this case is dictated by A and B and the summation. If that summation is higher and individually they are higher, that means that it is the prior that will govern your belief and it will not be the data you are getting. And it happens, right? There are many cases where we have much more experience, so one interaction does not change what we. So, like that. So, this becomes a strong prior in that case. Okay. So, A and B are hyperparameters and act as pseudo count. And then the strength of the prior is determined by A plus B, this count, this number. Okay. The strength is determined by this number and you can give it a number. We generally give, generally it is called N naught. It is like the number of pseudo experiments you have performed before observing anything. So, often we denote it as N naught. Okay. Now, as a special case, if A is equal to B equal to 1, your map estimate becomes equal to your MLE estimate, which is equal to NH by N. Okay. And this is happening because beta with 1 comma 1 is a pseudo prior. Okay. So, beta not a pseudo prior, sorry, is a non-informative prior, sorry, 1 comma 1 non-informative prior. There are other non-informative prior also which we will talk, like Jeffrey's non-informative prior, we will talk about that later. Even uniform in some cases, beta 1 comma 1 actually gives something like uniform. Okay. So, yeah. Okay. So, this is the, any question up to this?
Why it is not complete Bayes? Because we are using Bayes also, why it is in between frequentist and Bayesian approach? Map.
Why map is there, right? Map is there because, where is the map? Here. See, for doing map you do not need the normalizing constant, you only need that numerator, and numerator you can always compute. But if you have to do fully Bayesian, you need the complete distribution, which means integrating out the numerator to get the denominator. That 99.99% time not possible. For conjugate prior, there is no point doing map, because you can get the closed form solution of the Bayesian. But for non-conjugate prior, like sorry, for non-conjugate, for prior that are not conjugate, in that case getting the posterior is the most challenging part, and everything revolves around finding the posterior. You will see, we will talk about sampling method, getting samples and all those things which are expensive. Whereas in map you do not need to compute the complete distribution, just compute the numerator and based on that do the map. So, it is a balanced trade off between MLE and Bayesian. Bayesian is the best but most expensive. MLE is the least expensive, but all the issues are there. Map is like a compromise. So, that is the reason. Okay. Yeah. So, we will talk about non-informative prior. So, now let us try to do Bayesian. So, in Bayesian we have already done half of that. So, if we take the Bayesian root, then we already have probability of theta is a beta distribution with, I think this number was NH plus A comma NT plus B, something like that, right? This is correct. Okay. This is what we got. Now, let us now bring back the learning mentality. Now, what should be our objective? Is our objective to find out theta, or our objective is to predict? Generally in machine learning, our objective is to always predict. Given the data, can I predict? That is our objective in general. So, now if I transfer that into this, my objective will be that given some data, let us say tail, what is the probability that the fourth coin toss will yield head? So, it is more like prediction, and our objective generally is prediction, okay, at least in machine learning. So, the question is how to use this information now. Use this to predict. Okay. So, now can you tell me, when I am trying to predict, I will be trying to predict some probability. So, what am I trying to predict? Can you tell me first in words that I already told. So, can you tell me, and then in mathematical form, what am I trying to predict? In words I will tell you, I am trying to predict that given my data, let us say head, tail or something like that, what is the probability of getting the next coin toss to be either a head or a tail? That is what I am trying to predict. Now, how will you write it down mathematically? It will probability of what and something like that. So, what will it be?
Please explain.
I will explain one. What I want is that I have tossed the coin 3 times, 4 times, 10 times, okay, and I have collected data that looks like head, head, tail, tail, head, tail. Now, given that I want to toss the coin one more time, and I want to predict what I am going to get, right? How will I do that? Obviously, but what distribution? So, it will be probability of something, right? So, what is that?
Probability of x given theta comma d.
X given theta comma d. No. Probability of head, that is mu, but mu is what I don't want to get. I want to get probability of. So, what is the probability that next time I will get head? Think about it. Head is denoted by 1. So, this is similar to finding out, although you were very close, probability of x tilde, let us say tilde is my next prediction, and I want it to be head. So, then this should be equal to 1 given the data, not theta, because theta is a distribution, you have to integrate it out. Given the data, I said, right, given that I have observed head, head, tail, what is the probability that next one will be head? So, next one is head is from this one, given I have observed head, head, tail, which is my data. This is what we will have to find out, and this is known as the predictive distribution, because this is the distribution of the prediction I am trying to make. And now we are in the full Bayesian zone, this is the actual Bayesian thing. Okay. In Bayesian you do not get any predictions point wise, what you get is predictive distribution. So, this is the predictive distribution, and now you tell me how will I find it out. Now, you tell me using the sum and product rule I have to find it out. So, I want to find out probability of x tilde equal to 1 given d. So, what can you tell me how will I find it out using the sum and product law? Remember, I already have some information which is probability of theta given d, which in my case is equal to beta nh plus a nt plus b. So, this information is to be used obviously, because that is only how the data information is getting transferred. So, how will I do that?
We will introduce a theta in the conditional part and then integrate it.
Correct, but not in the conditional part. So, let us, yeah. So, integration of probability of x tilde equal to 1 given theta. Why am I not writing comma d? Because once you know theta, it is independent of d, because your probability of getting a head or tail is dependent on the probability of head mu. It does not depend on data any longer. So, that is why that part is not there. And the second part is probability of theta given data, and you will integrate out theta. Okay. And theta will go from what range? What is theta? Mu. What is mu? Probability of getting head, probability varies from. So, this integration should be 0 to 1, because its probability varies from 0 to 1. So, you are integrating over the total range. Okay. I will repeat this equation once more just to illustrate how the sum and product rule has been used here. So, what I have done here is, see, I want to find this one, right? Right? You will agree that this is equal to probability of you agree? The sum law. Now, I will break it using the product law. This is equal to integration probability to equal to x tilde equal to 1 given theta comma d multiplied by probability of theta given d. This is the product law. And now I said that once you condition on theta, they are conditionally independent. We talked about conditional independence, and since they are conditional independence, this term is not needed. See, now it matches. Now this thing you might feel that you are understanding until and unless you solve problem yourself, you are not. And so there is a homework. Once we are done, you have to repeat the same problem for Dirichlet distribution, which means for throwing a dice. So repeat the problem, find out MLE for throwing a dice, map for throwing a dice, and this Bayesian thing for throwing a dice.
Sir, for the second statement, which argument we used to write this statement?
Second one, product law. Product of A B is equal to A B given A. So A B given C is equal to A given C multiplied by B given A comma C. Okay, so let me write that down also. So we know that probability of A B is equal to probability of A, probability of B given A. We know that, right? So you can extend it A B given C. So everything will now have a C given, A given C, B given A comma C. Okay, so this is what I have used, and then I have said that okay, once you condition on C, A is becomes conditionally independent, so I have removed that. So this is what has been used. This is the product law only, but with a condition. Okay, clear? So this is how you can get. So let us find it out. What will I get? What is probability of x tilde equal to 1 given theta? What is the first term equal to? Let us call it equation, I forgot the name, it is 7. So from 7, okay, the rest of the thing was for your for explaining. So probability of x tilde equal to 1 given d is equal to integration. Tell me what is the first term? Theta, mu. What would have been the first term if x tilde equal to 0? 1 minus mu, coming from the Bernoulli distribution. So this is the likelihood, nothing else. Okay. So this is equal to, I will write mu. And what is the second term? Theta given d.
Which we have obtained
Beta, correct. Beta nh plus a comma nt plus b d mu, and mu goes from 0 to 1. Now is this expression ringing a bell? What is this expression? Expectation of mu with respect to beta distribution. So expectation of the beta distribution, right? And what is expectation of beta distribution? It is a by a plus b. So this is equal to expectation of mu, and expectation of beta distribution, you can find it out, is equal to a by a plus b, where the parameters are a and b. In your case the parameters are different obviously. So in your case what will be it equal to? What will it be equal to? nh plus a, that is my a, divided by n plus a plus b. Okay. And here I am using the property that expectation of beta a comma b is a by a plus b. This is the property that I used. Okay. So now let us take our non-informative prior. What was the non-informative prior? A equal to b equal to 1, right? Beta 1 1. What will I get? nh plus 1 divided by n plus 2. So I am not going back to the MLE estimate. So even with non-informative prior, when you do Bayesian and do the integration and do the complete thing, even that is giving you some information here. So what I was calling a non-informative prior is not a proper non-informative prior. A proper non-informative prior is a Jeffreys non-informative prior, which we will discuss later, where the Bayesian will become like MLE. Right now, I call beta 1 1 as a non-informative prior from the map perspective. But can we have a prior that will be non-informative from the Bayesian perspective? We will look into that later. Because it was going whatever, whenever something goes back to the MLE distribution, that is non-informative, but that was taking only map back to MLE. So, from map perspective, it was not giving you any additional information, but definitely it is giving you additional information from this perspective. And from this perspective, it will only be equal to MLE if A comma B is equal to 0, I mean A equal to B equal to 0, which I do not think is feasible because they are supposed to be greater than 0.
But in MLE we were estimating mu that was equal to NH of something. So here we are calculating the probability.
Exactly, true. That is that's why I am doing Bayesian. We are calculating probability of that, and that is coming out to be that. And when you get a probability, because it is a probability mass function, even that probability will become a distinct value. If it was a continuous, I will not get this kind of thing, I will get distributions now. That is what you are asking, and that is exactly correct. We will start getting distributions when we go into continuous variable. In this case also we are getting distribution, like we are getting distribution in terms of values, right, because it is discrete. But anyways, and when we do continuous, we will get distribution. Now, if you want a point estimate, one question will be what is better, should I do the map or something else. So, the better estimate is once you get the point, once you get the distribution, you can take the mean, predictive distribution, take the mean of that. Here it is automatically becoming the mean, but not every time. It is becoming the mean because for Bernoulli distribution, mean is equal to probability. That is the property that is coming out, right. For Bernoulli, that is the, I mean in this case it is beta, but for Bernoulli that is the property, and that is somewhere playing a role. So, just to summarize, right, I told many things in the last 2-3 minutes. One of the thing I am telling here is that beta 1 1 1 now is giving you some information, which is NH by NH plus 1 by N plus 2. So, this part let me separate out. So, expectation of mu with beta 1 comma 1 yields NH plus 1 by N plus 2. Okay. And this is known as one smoothing. This is, there is a name, one additional smooth. So, once, so you are kind of smoothing your thing, okay, by adding a 1 to both head and tail. It means that there is a, actually often what happens is that when you are doing experiments, I mean even without doing this calculation, you add a 1 to your number. So, you have observed, let us say 100 heads, you will count 101, you have observed 50 tails, you will calculate 50 plus 1, because you do not want the 0 thing to come, because this will never give you the 0 thing. So, that smoothing will happen, and that okay. Now, you can always ask why 1, why not 2, again that becomes a prior, right, because in this case the prior was like that, but that is a valid question, why 1, why not 2, why not 5, why not 1000, you can. The stronger is prior, then the larger that number should become. The worst case you do not have anything, 1. So, in that sense, okay. That means it is as non-informative as you can go in some sense, right. So, yeah, so this is the thing. I have 5 minutes, so let me wrap it up. So, to wrap it up, through this one example, I have introduced many concepts, which we will be seeing again and again throughout this course, starting from next lecture when we start prior. So, we have introduced, so through this example, we introduced the concept of, or we not only introduced, we showed actually, we solved MLE, how to solve it, what are the potential problems and all those things. We talked about map, how to solve it, what are the potential problem when map becomes equal to MLE. We talked about conjugate prior, which we will start talking soon. Okay. We talked about somewhat we started talking about prior modeling and the effect of prior, because we talked that if A and B are large, that has more influence if A and B are small compared to that. So, we did talk about influence of prior in some sense, in a very small sense, but in the context of this problem. So, we did talk about effect of prior, right. We talked about analytical solution, that is how to compute the posterior. In this case it was analytical, not always it will be analytical. So, we talked about posterior. What is posterior? There is a confusion here, let us see. What is the posterior distribution? No. Probability of what given what? Theta given d. Do not confuse it with the predictive, many people do. Okay. Posterior is probability of theta given d, predictive is probability of x tilde equal to 1 given d. So, there are predictive is also sometimes called as posterior predictive. So, that is the part you should be careful about. So, we talked about posterior and how to compute it, right. We talked about predictive, which is also known as posterior predictive in some books, many books actually. Okay. And we did all of this in the context of only the coin tossing example. For coin tossing example, you can do all of this in closed form, small things. That will not be possible when you start doing it for, let us say, a linear regression problem, a Gaussian process, a neural network. So, we will be doing only this thing, but now we will try to scale things up, and for scaling things we need to go in depth. So, we will be talking about prior in the next lecture. We will start talking about prior, and from there we will try to start scaling things. Once prior is done, we will start scaling things slowly but surely. One thing I did not cover, you can also use it to predict next 10 outcomes. Where is it? This one. If I have to predict the next 10 outcomes, what will change in this equation? So, I suppose I am interested in how many heads will I get in the next 10th row. So, I have binomial. What will become binomial in this? So, I want is that I have tossed the coin 4 times, I have got 3 tail 1 head. Now, in the next 10 toss, what is the chance that I will get 3 heads? That is binomial, you are correct, and that probability of x tilde equal to 1 given theta, that will become binomial, and that comes under the beta binomial distribution. Nothing changes, everything is same. Okay? Just the binomial will come, so the result will change. So, that will become, instead of Bernoulli, instead of theta that we got, we will get the NCX theta to the power. Yeah. P of theta given d we can take to be still be beta, because when you have performed the experiment, it is 1 at a time, and you are looking at so theta given d will not change, only the first one will change, because when you are having data, it is 1 at a time, but when you are predicting, you are trying to predict. If you are interested, look into these slides.
Sir,
We have the slides, yeah, one second. So, with the binomial you will get it here. So, all those things are here, you can look into the slides at the end. I will upload it, I have uploaded other slides. Okay. So, look into it. So, with that I will stop, I will take your question offline because there is class. Okay. Thank you.